Hello guys, welcome to the lecture 2 of machine learning and neural computing, right? So today we're going to discuss about simple linear regression, right? So basically we have to work in the recorded lecture manner due to these power cut issues, right? So I put up a forum link. You can post any questions regarding the lectures, right? Then you can then we can attend to those questions, right? Then we'll have a practical sessions on Friday, right? So you can discuss with the instructor and make some arrangement, right? So regression basically means like so there is a dependent variable and one or more independent variables, right? So basically, suppose we have some data points like this, right? So in here we basically try to come up with a function, or in this case a line that will most fitted to all these data points, right? That means basically it basically mimics all these data points, right? To get an line, right, we need to have some sort of a function, right? So in here we're going to find this function, right, that will mimic these data points, or these data points that will be most fitted to these uh, that function basically most fitted to all these data points, right? So if we consider this example on fresh graduates salary regarding, we discussed that in lecture 1, right? So if we consider this, right, we have this set of data points. These data points, like gathered, can be like through a questionnaire or a survey, we gather these data points, right? So we don't know how these data points generated, right? So now we're going to find the function, right? If we know the GPA value, right, then we can simply find the salary that person going to get, right? So these are the data points we gathered on some mechanism like a questionnaire or a survey, right? Then we going to find a function, right? If we find this function, then basically we can feed the GPA value. Suppose in this case GPA like 3, then we can simply get a value. Okay, this person will get around 1 lakh, right? So in the linear regression, we basically trying to find this function, right? So this function will gives output as a, like, it can be a real number, right? In this case it cannot be 0, but it can be a real number, right? So basically this linear regression is a supervised learning, that, and it's a regression, then that basically means as output we get some sort of a real number, right? So in here basically we going to do a fitting a line for a set of sample data. We have a set of sample data we gathered from some mechanism. Then we going to fit a line for that sample data. Then if we correctly fit the line, then we can predict future data, future values, right? If we find the exact most fitted function, suppose fx, right? If we find this function, then we can basically put any value, right? In this case suppose 3, then it will predict, okay, you will get 100,000, right? So that's the basic idea, right? So if you consider this same example, right, in this case, so the dependent variable is the salary, right? That's basically depend on your GPA, right? So the GPA is the independent variable, right? Then we're going to find a function called f that will basically take input as x, in this case a GPA, then it will predict the salary, right? So this is the basic idea behind the linear regression, right? So then these values, if you consider the actual values, the data points, right? that we collected from a survey or a questionnaire, right? So if we know this exact function, right? So that will be our that that's a kind of a name. We can give it as a target function, right? That is the target we're going to get, right? If we get the correct function that will mimics the all these data points, in that case, that function we can call it as target function, machine learning, right? Then if we consider these data points, there are we can basically draw so many lines as we discussed in the first lecture, right? You can have millions of line, right, for these set of data, right? So our purpose is to find the most fitted one or the target function that will fit to all these data points, right? Then that's our target, right? So since we can have so many functions, right? So in here, basically we call this function set of these function as hypothesis set, right? For each function here, suppose this is f, this is g, this is h, right? These are functions, and this will gives an line, right? We can call the each function as a hypothesis, right? So set of these hypotheses we can limit as capital H, right? These are the set of functions that basically mimics the behavior of our captured data or the sample data, right? So basically in learning in the machine, this regression problem, right? We have a set of data, right? So these set of data basically generated by a target function, right? We don't know this target function, right? We just have this set of data that are basically captured through a questionnaire or a survey, right? So there is a target function, right? So we're going to find this target function, right? From by now we don't know the target function, right? We just know that set of data, and we have set of hypotheses or the functions like f, g, h. We have set of functions, right? So what we're going to do is we feed the set of data and we feed the hypothesis, the set of hypotheses into our learning algorithm, right? That learning algorithm basically going to find the most fitted function or the hypothesis out of this set, right? So basically, our learning algorithm going to find this hypothesis in kind of like a very statistical way, right? So we feed the data and we feed the set of functions, right? Then our algorithm going to pick what will be the most fitted hypothesis for this set of data, right? So if we come up with the final hypothesis as G, that will be most of the time similar to our target function. It should be similar to like it should be nearly similar to our target function, right? We have set of hypotheses and we use our data, and inside this learning algorithm we're going to discuss this learning algorithm in the later part of the lecture, right? So for now, consider it as a black box, right? So we have an algorithm, right? Based on that, that algorithm will pick the most fitted hypothesis out of our set, right? So that's the basic idea behind this linear regression learning part, right? So when you consider this function, right? Suppose this is our function that will gives the relationship between our GP and the salary, right? So we can basically write it as something like this, right? This is the same as y equals mx plus c. You know these things, right? For here to get make it more like like statistical way, we basically replace this m with theta 1 and c with theta naught, right? So this is a linear relationship, right? So because of that, we have x in power of 1, right? So gx is our final hypothesis, right? If we feed the GPA value as x, then if we know the theta 1 and the theta naught, then gx will basically predict the estimated salary. So this x is the independent variable, the GPA value. Then gx will give the expected salary, right? That's our independent. That's our dependent variable, right? So if we know the final hypothesis, then we can basically feed the GPA value. Then we can basically find the estimated salary, right? So for now, we need to find this theta naught and theta 1, right? So if we can find this theta naught and theta 1, that basically means we cover all the data points, right? Then basically we are done with the data set. Now we know the function. Then if we feed the GPA values, that will basically give the estimated salary, right? So this is the basic linear regression means, right? So so how we going to decide this theta naught and theta 1, right? So suppose we have a set of we have a final hypothesis, we call it as gx, right? So hx is just one instance of our hypothesis set, right? So our basic intuition is to make this hx our one instance of our hypothesis to make it more closer to our y in our training data. So y is the expected salary, right? So we're going to make this hx closer to y, right? If we can make it so much closer to y, in that case, so if it is the most closer one in the for y, in that case, that becomes our final hypothesis, right? So we know, like, so this y is coming from our training data that we captured from through our questionnaire or a survey, right? So then this our hx basically give our predicted value, right? This is from our hypothesis. This is the actual value, right? So we need to make this difference very close to zero, right? If we can make it close to zero, in that case, it means it basically this hx mimics the y, y or the real value, right? So that means, so most of the time, there will be an error with our value that we get from our hypothesis and our real value, right? So this is the error, right? So this is the error, right? So if we can reduce this error, that basically means it's go towards the target function, right? So in this through our algorithm, learning algorithm, we going to reduce this error and find this theta naught and theta 1. So in here, basically, so if we draw a line for a set of data, right, you can see there is a error, right? So this is the error, right? We can call it as E1, right? So this is the difference between our hypothesis value and the actual value, right? So so the data points that are above this our hypothesis hx, those will give a positive error. As you can see, this is suppose this value is sorry. So this one basically gives an positive error, right? suppose our hypothesis value will give like 5 and actual value will look like 3, then if we subtract 5 from 3, that basically a positive value, right? So all the data points below our hypothesis gives a positive value, and the data points that are above our hypothesis basically gives a negative value, right? So there can be positive values as well as negative values, right? So these are negative values and these are positive values, right? So as you can see, so we need to reduce the whole error. So it can be either positive or negative, right? To cope up with that, we come up with these, right? So we're going to make a sum of square, right? So we're going to get the square. That basically means we get the value from our hypothesis, and this is our expect real value. Then we're going to make it power to the 2, right? In that case, those minus values will become positive values, right? So the positive value always end up in the positive values. Then the negative values also end up in the positive value, right? We just need the value of the error, not about the negative or the positive, right? So basically we take the error, e1 e2 like that, and we going to square this error and take the summation, right? We should consider all these data points, right? So our line should fit to all the data points, right? Because of that, we're going to consider all these data points and take the difference between our hypothesis and the actual value, right? So this will give E1, E2, E3 like that. So then we are make it take the square value, right? Like that you're going to get the summation, right? So this will give the final error, right? So in this linear regression problem, we're going to reduce this value for the whole error and make it in closer to 0, right? So if it's closer to 0, that basically means, so this our hypothesis or the line will fit or mimic all the data points, right? So this is a illustration of how this occurred, right? So as you can see, so this is our hypothesis colored in blue color, right? So it's try to fit the all the data points and come up with the line that will mimics the all these data points, right? First starting from somewhere else like this, then it will come to a place like that will fit to all these data positions, something like this. So if it is the final one, then we can tell that that's our final hypothesis that will move closer to our target function. So when we are selecting this theta naught and theta 1, right, we should keep that in mind, right? So these all the data points should be uh, like, suppose this is our hypothesis, right? So we should come up with this hypothesis to reduce this distance for each data point, right? That basically means this data point should be more closer to our hypothesis. That means we should reduce this distance, this error, right? The same thing, right? So so we should, as a one feature, basically we can consider one aspect, we can basically consider the sum of squared error, right? So we don't need to go one by one, right? We can get the summation of squared error, right? You can find the error then make it squared, then take the all the summation, right? So E1 plus E2, E3 like that. You can take it as a whole, and this is our sum of squared error, right? So if we reduce this, that basically means this line will most fitted to our data points. So when you're selecting this theta naught and theta 1, right? So this is our here we have our value that we basically get from the hypothesis, right? So I checks, and this is from our real value, right? So this is our hypothesis value, then this is our real value, right? To reduce the negative values, we basically make it squared, right? Then we consider all the data points, right? So it is the number of data points we have, right? We consider all these data points and come up with the one single value, right? So we should select this theta naught and theta 1 to make this value minimum, right? That's the basic approach, right? So we consider all the data points from 1 to n, right? That means hx1, right? That basically means hx1 minus y1. Then we hx1, right? So like that we take each array and make it square. Then we basically do this for all the data points hx2 minus y2. Then we make the square, right? Like that we going to consider all the data points and take the summation, right? So the summation should be minimum, right? So this value, right? So basically we can write it like this, right? So we call it as objective function or the cost function, right? That is from J, right? J is a function of theta naught and theta 1, right? So this is our hypothesis we had, right? So basically we have the cost function here, right? So we consider all the data points and subtract by the actual value and make it square, right? Then we have a constant called 2n, right? So the whole thing divided by 2n, right? So by dividing n, you can see it's basically averaging for the data points, right? So this 2 is just a constant, and n is also a constant, right? So this value, this portion basically depend on only on the our hypothesis, right? So if we uh, divide anything by a constant, that doesn't make any changes to our final value, right? It doesn't make any damage to our final function, right? So in the at this moment, you don't need to worry about this value, right? We can consider that in the later, right? So keep that in mind. So how to come up with the cost function, right? So cost function is a function of theta naught and theta 1, right? So it's basically theta naught plus theta 1 x. So this is our j, right? Then we can find the cost function like this, right? Hypothesis minus our real value and make it square. Then consider all the data points and make it a summation, right? This is our cost function, right? So if we can find the minimum value for this cost function, right? In that case, we are done. We know we've come up with the minimum, that we come up with the function that will give the minimum error, right? If it gives the minimum error, that basically means our hx will most fitted to the data points. So this is another example you can see, right? So you can see the error becomes reduced, right? So it basically calculating the distance to each data point from the hypothesis, and this hypothesis changing, right? Then by changing the hypothesis, you basically calculating the error, right? If you can change this hypothesis in a way to reduce the error, and if you come up with the lowest error hypothesis, and that's the uh, thing we need basically, right? So how are we going to get this minimum error given hypothesis, right? So basically our hypothesis we can limit as hx, right? Then our cost function, it's a j as a function of theta naught and theta 1. Our hypothesis only a univariate function. It has only one parameter, that is x, right? So it only depend on x, but j depend on theta naught and theta 1. So this is the learning process, right? So we're going to find the theta naught and theta 1 in kind of a formalized way, or the algorithmic approach, to reduce, to minimize the cost, right? So we have j function, right? We have j function theta naught and theta 1, right? If we can make it minimum, right, in that case our error becomes minimum, right? That means our hypothesis basically most fitted to all data points, right? So finding this theta naught and theta 1 is the learning process, right? We should come up with the theta 1 and theta naught for a minimum cost value, for the minimum error. For that, basically we are using this gradient descent algorithm, right? So we can start with any theta naught and theta 1, right? So we're going to do some repetitive thing until we get the minimum cost value in a way of decreasing the cost value, right? So we are basically updating theta naught and theta 1 in a way of decreasing this cost function. At one point you will get the minimum value, right? So it started from like here, right? Then again here, right? You are going, your cost value is making decreasing, right? At one point you will hit the lowest value, then again you will retrace from that and you will get higher values, right? You should find this exact point which gives the minimum cost value, right? So that value will given by this particular theta naught and theta 1. So initializing of this theta naught and theta 1, basically you can either start it from random values, right? Or you can start it from zeros, right? That's totally fine, right? So in here, basically you're going to, so this is the gradient descent algorithm, right? So here we have theta j, right? So you're going to update this theta j from a portion. So this alpha is some number, fractional number, right? Then here you have the gradient, right? So as you can see, so if we consider our cost function like this, right? So this is our cost function j, right? So if we derive this j function, you know, like if you're familiar with the derivation, right? So if you derive, so if you derive 1 times this j function, that will gives the gradient, right? So if you know the value, right, it will, suppose this place, right? Suppose this place is theta, what you call theta k, right? So for a particular theta value, right? So here we have theta, right? For a particular theta value, if we do the derivation of the j function, right? It will give the tangent for that particular place. That means, so this there'll be a tangent for this particular place, right? As you can see, now we go into like so we know the theta j value, and we going to update this theta j value, right, in a way of, so basically at the end of the day we should come to this place, right? So this place is the suppose this is theta z or something, right? So this is the place which gives the minimum cost or the minimum error, right? So this is our cost function. The function's minimum is here, right? Right. So we should find this specific point, right? So to do that, basically we can use this derivation, right? So you can basically find the derivation, then reduce that derivation. Suppose we were here, right? Then so we were here, right? From that we subtracting some portion like 0.25% of gradient out of this theta k, right? So in here the gradient is a positive value, right? So this is our 90% degree, 90 90 degree, right? Suppose this is about 75, right? That basically a positive number, right? In that case this theta k will uh, update into some place like here, right? So in here you can see, right, now the theta is updated into some place like here, right? Again you're going to draw a tangent, right, for that specific place, right? How to get the tangent? To get the tangent you can basically derive at that point, right? To get the tangent, and you're going to subtract some portion of value out of this theta, right? Again, so it's a positive number that it will again come to place like this. Like that you can basically do the subtraction until it converge, right? So if you are familiar with the derivations, you know, right? If you derivate a function, right, at one point it will gives zero either in the maxima or a minima, right? So in this kind of places, if you draw the tangent, so the value will be zero, right? So basically the gradient is zero, right? Now the tangent, basically the gradient is zero, right? If we know the place where it gives a zero value, right? In that case, so theta won't update, right? So suppose at this point theta is it, right? So theta is it, you're going to update theta is it minus alpha times. If you take the gradient, okay, now the gradient is zero because you are in a minimum, right? So if you draw a tangent for a minimum, right? So the gradient will be zero, right? So it's become zero, right? So T2 won't update, T2 remain as, sorry, TZ remain as TZ, right? So that's why it's come to the convergence, right? That's the basic idea behind this gradient descent algorithm, right? So first you find the gradient, then you subtract some portion of gradient like zero point 0.5 or zero point 0.1, then you update this theta, right? So you get the gradient and multiply with the fraction that will give some reduced value of the gradient, and you basically subtract out of this theta, right? So if it is a positive value, so the theta will update like this, right? So it will come back to a place like here, right? If it is a positive value, it will increase the theta and come to a place like this, right? Anyway, if you are come to the bottom or the minimum, in that case the gradient becomes 0, right? So the theta won't update no more, right? Theta is stopping the update because of the gradients become 0, right? So if you subtract 0 from any number, it's give the same number, right? In that case, so basically we can find the minimum out of our j cost function, right? That's the basic idea behind this gradient descent algorithm, right? If you are not clear, you can basically put some forum topics, then we can discuss, right? So this alpha, we basically call it as a learning rate, right? It has a kind of a huge effect when you find the minimum value and using this gradient descent algorithm, right? We can discuss these things, right? So this is the place we discuss same thing, right? So this is our tangent, right? So and this will have a positive uh, gradient, right? So if we update the theta, that will update into somewhere else like this, right? Then it will end up in a place like here because the gradients become 0, right? Theta won't update no more, right? Theta will remain as same. We can tell that okay, it's find some kind of a minimum out of this cost function. So this is an illustration of that. You can see we going to draw tangent out for each places, right? So we started from here, right? Then we come to this place here, right? And here you can see it's stopping the update at when the tangent become horizontal, right? At that point, theta won't update, right? In here, if you consider this part, this is our hypothesis, right? Hypothesis is basically generated depend on the cost function, right? So when the cost function becomes minimum, right? At that point, we will get the most fitted hypothesis or the target function, right? So this is another illustration. So this is a 2D plane now, the cost function, right? As you can see, it's getting reduced and come to the bottom. Then at that point, you will get the most fitted hypothesis for the data set. And this is another illustration, right? So it's starting from a higher value, then it's getting reduced and come to the bottom of the cost function. In that case, so our hypothesis will fit to the all these data points, right? If anyhow we can find the minimum error function, minimum error cost function, in that case that will give the most fitted hypothesis for the data set, right? So if you're not familiar with these derivatives and partial derivatives, you can simply go through this link, right? So when you are considering this alpha or the learning rate or the step size, right? So if we have higher large learning rate, right? If we have large learning rate, right? So that will basically jump like this, right? Because we are reducing higher portions out of our theta, right? At some point, theta was here, right? At one point, theta was here, right? Then you reduce a higher amount out of this theta, then it will again go back to somewhere else like this, right? So this will jump like this, and at one point you will miss the exact bottom, right? That means you will miss the uh, exact minimum, right? So if you make it very low, alpha is very small in that case, so you will have to uh, train for longer time, right? So this will slowly come to the bottom, right? So that's also not a good thing, right? So you can make it adaptive, right? For higher cost values you can have higher learning rate. Then we are coming to the lower cost values, then you can reduce the learning rate and find the exact minimum, right? So that's the effect of learning rate with the when you find in the minimum of the cost function, right? Then there is a thing called local minimum and the global minima, right? So if we consider a function, the function can be have places that will gives bottoms like this, right? So these are you can see it will come to a place and retracing, right? So these are, we can call it as local minimums, right? This is not the exact minimum of the function, right? So the exact minimum is the global minimum, right? So if you encounter some scenario like this, in case you have to find the minimum value out of these local minimas, right? Then you suppose you need to train several times, and you will get several minimums, right? In that case, you should pick the global minima. That means the exact minimum of the function, right? So this is a illustration, right? So starting from some place like here, then it will getting reducing the cost function, right? Then it will eventually end up in a global minimum, right? Either you can go in this way and end up in somewhere else like this, right? And this is the local minimum, and this is not the best option, right? So you can have a better option if you go in this way, right? So that's basically depend on the training, right? So either you can end up in a global minimum or the local minimum, right? You have to make sure you find the global minimum out of this cost function, right? So this is a global minimum and this is a local minimum. So if we come back to the gradient descent, right? So basically we know the j our cost function, right? We discussed in previously, right? In here we can basically substitute it with the cost function, right? So it's a function of x and y, right? So this is the final place where we can update the theta j, right? So you can simply substitute with the your cost function, right? Then you can do the derivation, right? So you know the cost function is coming from two thetas, right? So it basically j theta naught theta 1, so it's equal to theta naught plus theta 1 x, right? Here we have x, right? So it's a function of theta naught and theta 1, right? So in that case, if we are derivating something with the two parameters, right? If you have two variables for a function, right, you have to do partial derivations and come up with the values, right? So this one for the theta naught, right? If j equals 0, right? So we need to do the partial derivation from theta naught, right? So if you take the partial derivation of this, right? So you will end up in the place like this. So I'm not going to do the calculations, right? You just need to keep that in mind. So this kind of thing will occur, right? So then if we derivate from theta 1, right, the partial derivations, then you will end up in a place like here, right? So you need to do the updates for theta naught and theta 1, right? Because of that, you can't do the derivation directly, right? You have to do one update for theta naught. To do that, you need to get the partial derivatives, right? You need to derivate from theta naught to update theta naught. Then you need to derivate from theta 1 to update theta 1, right? So this is the final algorithm, right? So you can simply update theta naught by this, right? Then you can update theta 1 by this, right? So you need to do this until it's converged to some place, right? So it will converge on theta naught, right? Then it will eventually converge on theta 1, right? In that case, you will get the uh, your target hypothesis, right? So this is the batch gradient descent algorithm, right? So this is the end of the linear regression, right? So in here, if we consider the cost function theta naught, so this is theta naught theta 1. It's a function of theta naught plus theta 1, right? Right. So this function is doesn't need to necessarily a linear one, right? So this model is, so this is our model, right? This model basically linear in theta parameters, right? You have theta in power of 1, right? So we have a model is in linear theta parameters, right? But you can have like theta naught, theta 1 x, theta 2 x squared, right? Like that you can have values, right? If we consider the theta values, that is linear, but if we consider the x values, you can see it's in the polynomial, right? So this is the basic idea, right? So linear regression means it's linear on the theta parameters, the parameters of the cost function, right? But it can be a polynomial in the sense of x variable, right? So basically you can fit a line for a data set of, if you have set of data points like this, you can fit a line for that, right? Either you can fit a curve, right? So either you can have a periodic function as well, right? So it's not about the straight line, right? So our model is in linear, right? Model is in theta values that are linear. That means theta to power 1, right? Theta to power 1, theta 1 to power 1, like that, right? But in the sense of x, we can have x to the power 1, x squared, x cubic, like that. You can have your cost function, right? The sense of the theta, that's linear, right? So that's the end of linear regression. If we have a quick recap, right? So firstly, we need to have a function that mimics set of data points that are collected from some like questionnaire or a survey, right? So for that, so need to come up with the hypothesis, right? So if we know the error between your hypothesis and the actual value, right? Then if you are reduce that error and come to a minimum value, right? In that place, we are done, right? To find this minimum error in the cost function, to find that you can basically use the gradient descent algorithm, right? You can find the gradient, right? You can find the gradient and reduce some portion out of the theta and update the theta. So the theta will update like this and end up in the minimum, right? So that is the gradient descent algorithm, right? So when you are using the gradient descent algorithm, you should keep that in mind about the alpha. If you make the alpha larger, then that will have one this kind of effect, and you will miss the x at bottom. If you have a smaller alpha, in that case, you will have to spend a lot of time to come to this bottom, right? Then the global and local minimas and this substitution, right? Don't worry about the mathematical parts, right? We know that like you are not more like familiar with the mathematics, right? But keep that in mind. You have to do partial derivatives to update theta naught and theta 1, right? If you have more values like theta 3, theta 2, like that, so you have to do the same thing, right? We can discuss in the next lecture, right? So this linear regression basically linear on the theta aspects, right? Our model is linear, but our hypothesis doesn't necessarily be to linear, right? It can be a polynomial one. Okay, guys. So we'll discuss the rest of the lecture on the next video.